All right, good morning, everybody. Good morning. Hope everybody had a good Thanksgiving. All right, a couple of things that I need to go over before we start. We don't have time to cover chapter 14, so just ignore it. I'm going to incorporate a few bits and pieces today and Wednesday on chapter 14 as we go along, because it's really derivatives of carboxylic acids. But I decided to sacrifice that. We took a couple of days that weren't originally planned in the syllabus to get caught up and to do some review and different things, and so it's just the way the ball bounces. And but you do need chapter 18 before you get to biochem, so that's why we're going to cover it. We'll start on it today as well. I am not going to have you do, we won't have quizzes over 13 and 18 like we normally do. We'll have some things in class that we'll do that I'll count as your quiz. Having said that, you still need to do your homework in there, because I am going to pull a few questions that were assigned from 13 and 18 on the final exam. Okay, so I will convert them somehow into multiple choice questions. And so since those are part of your handwritten notes, that is something that you can come to the final exam with. Okay, so we'll talk more about the final exam on Wednesday. The only day that I really have to where I can give you all a review would be this Thursday evening. So I will schedule that and we will record it. And so I'm sorry, but I will actually not be here during the final exam. I've got a conference that I'll have to be at. So the final exam will be proctored. I'll get back the next day. I'll grade the final exam. I'll post the grades, and if anybody has any questions, they're certainly welcome to, of course, come and talk to me. So any questions about that? All right, well, let's go ahead and get started on the stuff that we need to talk about. So we're going to talk about carboxylic acids to start with. And as the name implies, these are acidic molecules. They're actually very strong acids from an organic perspective, but they are weak acids from your Gen Chem perspective. Okay? So you might remember from Gen Chem that a strong acid is something that you put in water and it completely dissociates into its ions. That is not what happens with a carboxylic acid for the most part. Okay, so this is the general structure of a carboxylic acid. We've already talked a little bit about the IR of these. We know kind of where we could see these in an IR spectrum, right? It's this hydrogen that is the acidic hydrogen, right? That hydrogen can be removed pretty easily through an equilibrium, which we'll talk about in just a minute in more detail. And of course, we can draw a resonance structure for the carboxylate anion. And it is this ability to draw equivalent resonance structures that accounts for, in part, it accounts for the acidity of these. These are much more acidic than alcohols, right? You might look at that and say, well, that looks like an alcohol connected to a carbonyl. And it kind of is, but remember, it's the whole piece is the functional group. And the reason is because these are resonance delocalized, and so it really is one functional group. It's not two functional groups stuck together. It functions as its own functional group. And the ability to draw these resonance structures means that it's much more stable than what you would typically expect, and therefore much more acidic. It's much more willing to give up its hydrogen. You will see these drawn either with the stick diagram. You will also see some places where they'll write it COOH, and you'll see some places where they write CO2H. You need to know that all three of those are carboxylic acids. Okay? COOH is not a carbon, single bond oxygen, single bond oxygen. Okay? This carbon would not have enough hydrogens to fill its valency, right? So this and this and this are all equivalent. Okay? A little bit on naming carboxylic acids. Okay? Carboxylic acids are named as oic acids. You drop the suffix and you add OIC, so it's oic. So like benzoic acid, propanoic acid, etc. Now, one of the things that you're going to find in carboxylic acid chemistry is that they are fraught with common names. For the purposes of this exam, you do not need to know the common names, but I'm going to let you know what they are as we go along. Because as you move into biochem, as you talk about things in maybe your nutrition classes or whatever the case may be, you're going to be haunted by the common names. Okay? So if we look at this simple molecule right here, this is 3-methylbutanoic acid. Notice there are 4 carbons in the longest chain, including the carbon of the carboxylic acid. 1, 2, 3, 4. So there's the longest chain. Okay? Notice it's 3-methylbutanoic acid, not 2-methylbutanoic acid. Why is that?
Because the first carbon is on the COOH.
Now, why does that matter?
You count the number of the carbon from that carbon.
It turns out that the carboxylic acid, because the carbon belongs to the longest chain, also takes priority. Okay? If I remember my reasons for the rules right? So, the carbon of the carboxylic acid is almost always the first carbon. Okay? It trumps the other functional groups that we've talked about. Here is trans-3-phenylpropenoic acid. Enoic. Why do we have enoic here? Because of the double bond, right? So it's like an alkene, right? So it's propenoic acid. Notice it's 3-phenyl. That's a benzene ring. So 1, 2, 3, right? And it's trans because we got the trans double bond. This is also known as cinnamic acid. Where do you think that comes from?
Cinnamon.
Mm-hmm. So it is a derivative of cinnamaldehyde, or it's oxidized cinnamaldehyde, which is present in cinnamon. Okay, so again, these common names. Notice here, 5-hydroxyhexanoic acid. 1, 2, 3, 4, 5, 6. 6 carbons in the long chain. It's going to be hexanoic acid. And we've got 1, 2, 3, 4, 5. We've got a hydroxyl group on carbon number 5. So it is 5-hydroxyhexanoic acid. This is 4-aminobutanoic acid. Again, 1, 2, 3, 4. Okay? This is an amino acid, and we're going to talk about those in chapter 18 as well. And then here we have what's called 5-oxohexanoic acid. It's oxo because of the ketone. Okay? Don't worry too much about that, but that's at the 5 position, and it's a carboxylic acid. Okay? Again, a lot of common names. Oxalic acid. This is ethane dioic acid. What's the di mean? 2. That's right. Ethane, we've got 2 carbons in the longest chain, 1, 2, and it's dioic acid. No, we don't have to use any numbers, right? Because it's the only places it can be, right? So numbers are irrelevant here. Okay, so this is ethane dioic acid, but nobody calls it ethane dioic acid. I can tell you right now, this is called oxalic acid. And if you were to come to my lab and you'd ask for ethane dioic acid, my graduate student might look at you kind of funny. But if you said oxalic acid, oh, I know where that's at. He can go find it for you. We can add carbons in between these two carboxylic acid functions, and now we have propane dioic acid. This is known as malonic acid. Okay? This is an acid that we use an awful lot in my laboratory for our chemistry. We do almost all kinds of stuff with so-called malonates. We never call it propane dioic acid. Okay? Even though that's the correct name. Butane dioic acid is also known as succinic acid. Pentane dioic acid is called glutaric acid. And then, of course, hexane dioic acid is also known as adipic acid. And it's this type of acid that's used to make a lot of plastics and other things. But they never call it hexane dioic acid for whatever reason. These common names have stuck. Also, you will find quite frequently that the Greek alphabet creeps in here. Okay? So if you think about the numbering system, right, the carbon of the carboxylic acid or the carbonyl carbon is going to be always carbon number 1. 1, 2, 3, 4, 5. Okay? But the carbon that's directly attached to it, we call that the alpha carbon, beta, gamma, delta, and so on and so forth, if you know your entire Greek alphabet. I don't know the entire Greek alphabet. I go out to about delta. That's about as far as I go. Okay? And so sometimes you'll see this. So this so-called 4-aminobutanoic acid, biologically, if you go into your biology class, they never call it 4-aminobutanoic acid. They call it GABA. Gamma-aminobutyric acid. Okay, it's a common name, but it's a common name that's pretty important. GABA is a biologically relevant simple amino acid that's used in a variety of processes. Okay? Some physical properties of carboxylic acids. When you have a pure carboxylic acid in the liquid state, or even in the solid state, I should say, in its pure state, let's just say that, they will exist as a dimer. Okay, they hydrogen bond with one another. You'll notice that you've got a hydrogen attached to an oxygen here, right? And so that hydrogen can hydrogen bond with the oxygen of the carbonyl, and this hydrogen of the other carboxylic acid can hydrogen bond to the oxygen of the other acid's carbonyl group. Okay, this is how they exist in their pure states, either liquids or solids. And so this has the effect of actually impacting their physical properties. Carboxylic acids typically have higher boiling points than you might imagine for a given molecular weight. Okay, so in this case, this is acetic acid, hydrogen bound as a dimer, and its boiling point is actually pretty high. You have to put quite a bit of heat in it to boil this because of this dimeric structure. Okay, so they like to hydrogen bond quite a bit. Okay, they can also be soluble in water or not. They do follow typically that 5-carbon rule. So carboxylic acids that have 3 or 4 carbons total in them per carboxylic acid group tend to be very soluble in water. Makes sense. Vinegar has acetic acid in it. You don't see 2 layers. It dissolves perfectly fine. However, you can start to get a lot of carbons on there and actually get to where you have something that is very low solubility in water. This is called decanoic acid. So deca, how many carbons does this one have just by the name? 10. Yeah, so it's a 10-carbon acid. We start to call these things fatty acids. The more carbons you add to a carboxylic acid, you start to change the way you talk about them. You stop talking about them as simple organic molecules and you start using the words like fatty acids. What do y'all know about fatty acids?
Cell membrane.
Cell membranes, yeah, cell membranes have fatty acids. Anything else? Anybody ever make soap? Lye soap? That is a fatty acid. It's a salt of a fatty acid, but these things are used in soaps because you have this nonpolar tail, as we like to call it, which looks like grease. That's why soap dissolves grease, is because it has this grease-like structure. But then it also has this piece at the front that likes water. That's why soap works. It's got a piece of it that likes water. It's got a piece of it that doesn't like water. It forms these things called micelles and surrounds dirt and grime and carries it into the water. Okay? So the more carbons we have, the less soluble the carboxylic acid will be in water. For those of you in biology and for those of you in nutrition kind of areas, you may talk about things called lipids. Lipids are nothing more than fatty acids. Okay, their carboxylic acids are their main functional group. We can have saturated and we can have unsaturated lipids. Okay, this is arachidonic acid. What other functional groups does it have? It's got the carboxylic acid, right? But what other functional groups are there?
Alkenes.
Alkenes. That's all it has, is a carboxylic acid and 1, 2, 3, 4 alkenes. Okay, this is called arachidonic acid. In biochem, they may call it arachidonate. Don't worry too much about the difference in nomenclature at this point. But this little molecule right here is responsible for an awful lot of things that go on in your body. Okay? Arachidonic acid gets converted into a thing called prostaglandins. Prostaglandins signal things in your cells. Prostaglandins cause you to have fever. Prostaglandins cause you to have pain and arthritis. When you take ibuprofen, ibuprofen sits in the active site of an enzyme that takes arachidonic acid and converts it to these other things. So it shuts that process down. When that happens, your pain goes away, your fever starts to decrease, etc. Would you call this a saturated or an unsaturated fatty acid? Yeah, it's unsaturated. And what's kind of unique about the double bonds?
All of them are cis.
They are all cis, right? So would you anticipate this to be a solid or a liquid at room temperature? It is a liquid. Yeah. So it is a liquid at room temperature because the cis double bonds put little kinks in the chain and it can't pack very well to make a solid, okay? And so it turns out that nature really likes, for whatever reason, to make these cis alkenes in these fatty acids. This is oleic acid. This is linoleic acid. These are the two principal, although not only, but the two principal fatty acids that you will find in olive oil. Okay? Now, they're not as carboxylic acids in the oil. They're actually as esters, which we'll talk a little bit about later. They're derivatives of carboxylic acid, but this is the acid that's responsible for making the ester. Okay, so these fatty acids are present in olive oil. Palmitoleic acid, oleic acid. What can you tell me about this one that's kind of different?
It has one bond, double bond.
Okay, and what about that double bond? It is, it's trans. What do we know about trans fats?
Dangerous for you.
They say they're dangerous for you, yeah. I think there's probably growing evidence that trans fats probably lead to atherosclerosis or heart disease, however you want to work it out, right? And so these things are not common in nature, but they are common in partially hydrogenated fats. So, to make vegetable oil solid, what you have to do is you have to take these types of things and you have to partially hydrogenate them. But during that hydrogenation process, it turns out that some of the double bonds get isomerized to the more stable trans double bond. And these things can actually form solids quite easily because they kind of start to look like saturated fatty acids in terms of their shape. And what do we know about saturated fats? They're typically solids. That's right. So that's largely believed to be the reason for the chemistry. Okay. So lipids are another name for fats. Okay, but they're composed of carboxylic acids. Now, let's make that. This is what happens when you take acetic acid and you dissolve it in water to make vinegar. Okay? Vinegar is about a 5%, I think, solution of acetic acid. When you place the carboxylic acid into water, it partially dissociates. Doesn't completely dissociate. It's in equilibrium. Okay? What do we know about equilibrium? What does it mean to be at equilibrium?
The rate of reaction is equal both ways.
Yeah, so the rate of the forward reaction is equal to the rate of the reverse reaction. That's certainly true. That's a true statement of equilibrium. But what else? Make it simpler. What does it mean to be at equilibrium? Pardon? Balance. Okay, I like that word. What does that mean here? both sides are equal. Not necessarily.
The ratio between the product and the reactant is consistent.
That's right. So it doesn't necessarily mean that you have one of these and one of these. Okay, that's not necessarily what balance means. But what it means is that when I first start off and throw this into water, at the very moment I do that, none of the carboxylic acid has dissociated, right? And it's sitting there all as the carboxylic acid. So you have all of this and none of this. But as time goes on, some of this starts to dissociate and make the anion. And some of the anion picks up a proton and goes back to product. What it means to be balanced is that that ratio is constant. It doesn't change anymore. And we represent that by what's called an equilibrium constant, KEQ. Okay? So KEQ is equal to the products over the reactants. Do y'all remember that from Gen Chem? Some of you might remember that, right? Equilibrium constants are the products of the products over the products of the reactants, right? So product meaning multiplication, right? So you take the concentration of the carboxylate times the H3O plus concentration, divide it by this and water, okay? Now water is one of the reactants here. Water, right, will pick up one of these protons to give H3O, okay? Does anybody know what the concentration of pure water is?
Concentration,
Yeah, what's the concentration of pure water? If I gave you a liter of pure water,
7.
what would its concentration be? No, that's the pH of pure water. It is 7. But what's the concentration of pure water?
I don't know an exact number, but I know it's a lot.
It is a lot. Anybody want to take a rough guess? How would we figure that out? What numbers do I need to figure out the concentration of pure water?
The moles.
I need to know the moles of water that are in a liter, right? How can I get to that? What do I know about water?
18 grams per mole.
18 grams per mole, right? Oxygen is 16, 2 hydrogens, that's 18. That's good.
And water is 1 grams per milliliters.
Yeah, so the density of water is 1 gram per milliliter at room temperature, right? With that information, you can figure out what the concentration of pure water is. That turns out it's around 77 molar. It's very, very concentrated, okay? Water's about as concentrated as you can get. Now, if I throw in a little bit of acetic acid into pure water, did I really change the concentration appreciably of pure water?
No.
Not really, right? I mean, I may throw, let's say I throw in 0.01 moles of acetic acid. Water's concentration's relatively stayed the same, so it's not changing too much, okay? So under these conditions, we can actually do something with water. We can pull it out of the equation. Now, you all probably learned in high school or in Gen Chem incorrectly. People say, well, since water is a pure liquid, it just falls out of the equilibrium expression. That is absolute, utter nonsense. There's no such thing as, you can't take an equation and just drop out one variable, right? It's the whole thing called the equal sign. Whatever you do on one side, you got to do on the other. And I always hate that when chemistry instructors go around and say, well, it's a pure liquid, it just falls out of the equation. It's nonsense. But since it is a pure liquid, and because it is so concentrated, and since it doesn't change very much, we can do a little math trick. And we can lie a little bit. Okay? And we can say that since it doesn't change very much, we're going to take this side of the equation times H2O, and we're going to take this side of the equation and multiply it by the concentration of H2O. And we're going to do that, and we're going to call that magically Ka, the acidity constant. Okay? Ka, the acidity constant, is not equal to KEQ. It is equal to KEQ times the concentration of water. Okay? But chemists never really talk about acids in terms of KEQ. We talk about them in terms of Ka. Okay? So it's the acidity constant. And here, the acidity constant is equal to this times this divided by this. Water looks like it has fallen out of the equation. but it hasn't. We've just combined it all into Ka, okay? And this is what chemists deal with all of the time. So for a strong acid that you think about from Gen Chem, what would the value of Ka be? Approximately, a range. What do you think?
10 to the negative.
If I throw an acid into water and it completely dissociates, these numbers would be large, right? What about the denominator? Would it be large or really tiny? Do I have much of my starting acid left?
No.
No, so it'd be really tiny, right? So you'd expect the value for Ka to be really big, almost infinitely big. Well, it's not, right? There's limits to this, right? For a weak acid, however, what would you expect the values of Ka to be? Right? If I throw a weak acid into water, which acetic acid is a weak acid, what does it mean to be a weak acid? When I throw it into water, very little of it dissociates, right? So what would these numbers be? Big or small?
Small.
And what would this number be? And any small number divided by a big number is a
Fraction.
tiny, tiny, tiny number, right? And it turns out that for organic acids, these numbers are typically quite tiny. 10 to the negative 4, 10 to the negative 5, 10 to the negative 6. Tiny numbers, okay? And so chemists, when it comes to math, organic chemists are about as lazy as it gets. It's the reason I'm an organic chemist. I took a lot of math, but I didn't really like and enjoy doing it. So I said, I'm going to become an organic chemist, okay? And so to make the math easier for us, so we can deal with it in our heads, this was, all before we had computers that could do everything for us, we convert Kas into what are called pKas, okay? And so we're dealing with really good numbers here when we do this. And to pKa something means just to take the negative log of whatever it is, okay? So the pKa is just taking the negative log of the Ka number, okay? Well, if you take 1 times 10 to the negative 4, and you put that into your calculator, and you hit log and then the minus key, you get 4. I would much rather deal with 4 than 1 times 10 to the negative 4th when I'm doing my math. Okay? And it turns out that carboxylic acids, for the most part, are going to be between somewhere around 4 and 5 in terms of their pKa. Okay? What were some pKas for other organic molecules? If you remember back to chapter, 2 or 3, when we talked about acids and bases a little bit? Anybody remember? Alcohols. You remember what pKa for an alcohol was? Approximately?
15.
Yeah, about like water, right? So they're around 15, 16. So 15 or 16 versus 4. That's a huge difference, right? How about something like just a hydrocarbon, like methane? What's the pKa?
30.
Pardon?
30.
Too low.
No.
Too acidic.
50.
50. Yeah, it's around 50. Very, very non-acidic, right? And we learned about the different things that contribute to acidity. Remember that? Right? And so, but it turns out that these carboxylic acids are about where, about 4 to 5 is what you're going to find for most carboxylic acids. Now notice I say for most, because we can actually do things that change the acidity of carboxylic acids. For example, we can add electronegative groups, things like chlorine or bromine or fluorine, to the organic molecule, and that increases the acidity. So if we look at acetic acid, right, just vinegar, acetic acid has a pKa of 4.76. It's a pretty good acid as far as organic chemistry is concerned. But if I replace one of the hydrogens on the alpha carbon with a chlorine, notice what happens. Now I've got chloroacetic acid. What happened to the pKa? It went in what direction? Up or down?
It went down, which means it increased in acidity.
That's right. Remember, the lower the pKa value, the stronger the acid, right? And that's, 0.9 units, right? And remember that every unit of pKa is a 10-fold difference. So this is not quite tenfold more acidic than acetic acid, but it's getting close. Now I take one of those hydrogens and I replace it with another chlorine. Now I have dichloroacetic acid. Look what's happening to the pKa. It's 1.48. And then when I replace the last hydrogen with a chlorine, now I have trichloroacetic acid. It has a pKa of 0.7. So as I add more and more electronegative atoms to a carboxylic acid, I am going to expect that that acid will increase in strength, or the pKa will decrease. Okay? Now you'll notice that in this example, we're replacing all of the hydrogens on the alpha carbon because that's all acetic acid has, right? It's just got the alpha carbon. But what if you have butanoic acid, right? So we have 1, 2, 3, 4. So we have an alpha, beta, and a gamma carbon, right? So if I take 2-chlorobutanoic acid, right, that has a pK of 2.83, very similar to chloroacetic acid, right? And you would expect that because we're just replacing one of the hydrogens with a chlorine, same as we did here. But now if I move that one chlorine over one carbon, notice what happens to the pKa.
Gets less acidic.
It gets less acidic. And then when I move it to the 4 position, it becomes even less acidic. It starts to get closer to the normal pKa value that we see for butanoic acid, right? So what's important is that the electronegative group has to be pretty close to the carboxylic acid functional group. Okay? And that makes sense. Why does that make sense?
The induction effect just doesn't reach that far.
Okay, but what does that mean? What does that mean? You're not wrong, but what does it mean? Right, so so if I have the chlorine here, right, that electronegative chlorine is closer to the negative charge. I think that's what you mean, right? Chlorine wants to pull electrons to itself. It can do it a lot easier when it's close than when it's far away, right? So these effects are distance dependent, okay? Pretty important impact on the acidity of these molecules. Okay? Now we can use the acidity of carboxylic acids to our advantage. So here's an example where we have what's called benzoic acid. Okay, so it's benzene carboxylic acid. We call it benzoic acid. Okay? This doesn't have much solubility in water. Why?
Big group, a lot of carbon.
Yeah, so we have one functional group that can participate in hydrogen bonding. And how many carbons?
7.
Total of 7. It doesn't satisfy our 5 carbon rule, right? So we would expect that this molecule will be insoluble in water, or only slightly soluble. But carboxylic acids, being acids, they will react with bases like sodium hydroxide, right? And so when I take this benzoic acid and I react it with sodium hydroxide, I get this molecule called sodium benzoate. Anybody know what sodium benzoate is used for?
Preservative.
Yeah, it is. Look on the back of your soy sauce next time. You get a packet of soy sauce somewhere. It will most likely say preserved with sodium benzoate. Okay? So it's a nice preservative. And it's water soluble. Okay? Why is this water soluble and this is not?
It's ionic.
It's ionic. We know that ions typically like to dissolve in water, right? It's a sodium salt. Think back to Gen Chem when you did the spot tests. What did you learn about sodium salts? They didn't form precipitates, did they? Right? They were typically highly soluble in water, okay? And so by making salts of these carboxylic acids, you can make them much more water soluble. And we can use this to our advantage to separate carboxylic acids from other compounds. So here's an example from your book where you're taking benzyl alcohol and benzoic acid, and you've got a mixture of it, and you want to separate these two things. So what do we think the pKa of the benzoic acid is going to be approximately?
4 to 5.
It's going to be somewhere between 4 and 5. What do you think the pKa of the benzyl alcohol is probably going to be?
16.
15, 16? Okay? So this is a strong acid. This would be a very weak acid, relatively speaking. So what you would do is you would take this mixture of benzyl alcohol and benzoic acid and you would dissolve it in something like diethyl ether. Both of these things are going to be soluble in diethyl ether. Benzoic acid is an organic molecule. It should be soluble in ether. And benzyl alcohol is an organic molecule. It should be soluble in ether. Okay? So you've got it sitting in a flask. You've got this ether solution of this mixture. Okay? Now, you add 1 molar, or 0.1 molar, sodium hydroxide. Sodium hydroxide is a base, right? Is it going to react with the acid or is it going to react with the alcohol?
Yes.
It's going to react with the acid. And when it does that, the acid's going to convert into the benzoate. So what's going to happen? The alcohol is going to stay around in the diethyl ether, and the benzoic acid is going to get deprotonated and end up in the water. Okay, so water and diethyl ether, do they mix with one another?
No.
They don't, right? It's like oil and water. Literally, it's like oil and water, right? And so you will have the diethyl ether layer on the top that contains the alcohol, and on the bottom layer you will have the water with the benzoic acid. Okay? Shake up this. We use a special flask called a separatory funnel. You shake it up. You let this layer separate. You drain the lower layer off, right, which has your water layer containing the sodium benzoate. But I don't want the benzoate. I want the carboxylic acid. So then we acidify it with really strong acid, 0.1 normal HCl, and that converts it to the carboxylic acid, which is insoluble in water. So what happens?
Separate again.
It separates out. It forms a precipitate, a solid. And you simply filter that solid off, and you have your pure benzoic acid. You then take the ether layer that contains the alcohol, you simply evaporate off the ether, and you've got your alcohol and the, you've now separated those two compounds. How would you draw the mechanism? So if I take benzoic acid, and I react that with sodium hydroxide, and I get sodium benzoate, how would you draw the mechanism?
The hydroxide of hydroxyl group acts as an electrophile, just attacking the hydrogen as a base.
It's a base, and all bases are what? Or all
Nucleophile.
nucleophiles are bases. I should have said it the other way around, right? So this is going to behave like a nucleophile,
Yeah.
right? Except it's not. It's going to act as a base, right? Is that all I have to draw?
No, the bond between the oxygen and the hydrogen.
What happens to it?
The electrons go to the oxygen.
Yeah. So that's the mechanism for the deprotonation of a carboxylic acid using a strong base. Notice I did not draw this as an equilibrium. Why did I not draw this as an equilibrium?
Because it's favored.
In fact, we say it goes to completion,
Yeah.
right? We say it goes to completion, so there's really not a back reaction here. This is a weaker base than hydroxide. This is a weaker acid than benzoic acid. And remember, the equilibrium always favors the weaker acid, weaker base pair. And a rule of thumb, this is not a law, but a rule of thumb, if the pKa differences are 5 or greater, you typically say that it goes to completion. All right? So I know that the pKa of water, approximately 16, and I know that the pKa of the carboxylic acid here is around 4. That's much greater than 5, isn't it, when I look at those differences? So I know that the equilibrium is going to lie to the right by a lot. Okay? So that's why that works the way that it does. Oh, there we go. Any questions about that? All right. So let's talk about some of the reactions of carboxylic acid. So here's an example, right? The first step is exactly what we just did. Right? We just generated the anion of the carboxylic acid. These will be referred to as carboxylates. Okay? And so that oxygen has a negative charge. Things that are negative charged typically make decent nucleophiles. Carboxylic acids can also be decent nucleophiles. And so we can react with things like alkyl halides. In this case, we're reacting it with iodomethane. And you get a new carbon-oxygen bond. Okay? This functional group is called an ester. Esters are how your body store fats. For those of you in nutrition and other things, you probably have called these triglycerides. It's just, we all have different ways we name the same freaking thing. I don't know why, but we do. Okay? But they're just esters. Okay? So, this is going to function as the nucleophile. This is the electrophile. How would I show that mechanism? Where would I push my arrows? Where would I start?
From the negatively charged oxygen
Okay?
to the carbon,
Okay? And then what?
and then the iodine bond snaps off.
Yeah. What's that reaction? What's the name of that reaction? What type of reaction is that?
SN2.
It is an SN2 reaction. Yeah. We've already talked about SN2 reactions before, right? So carboxylates will react with alkyl halides to form esters, right? This is a two-step process, okay? Notice you take the carboxylic acid, the first thing you have to do is react it with sodium hydroxide to get the nucleophile. Carboxylic acids by themselves are pretty poor nucleophiles. They're not charged. This is a much better nucleophile. So you react it with sodium hydroxide, you make this. Then you throw in the iodomethane, you shake it around, and you get the ester, okay? Does anybody know what carboxylic acids kind of smell like?
They smell bad.
They smell what? Burned. Some of them might have kind of a burned smell to them.
I want to crispy.
Not quite crispy. But they can have a little bit of a burnt smell. A lot of people kind of say they smell acidic, but that doesn't really describe what we're looking for, does it? What does that mean? What does vinegar smell like?
Strong.
Strong pleasant, strong not pleasant?
Not pleasant.
Not pleasant. It's not something you'd put behind your ears before date, is it? Right? You wouldn't grab the vinegar and do that, right? Well, what do you know about esters? What about the smell of esters?
They smell sweet.
They do smell sweet.
That's what they call esters of the old lady.
Yeah, I don't think that's right. But if you want to believe that, you go right ahead. Yeah, so this actually turns out to be this molecule, not what's in the box, the whole molecule. This is called methyl benzoate. This is an ester, and it is the scent of the snapdragon flower. So if you've ever smelled a snapdragon and you went, that smells pleasant, it's because of the ester. All of your colognes and perfumes, for the most part, contain esters. Flowers make esters. okay? And they smell good. Anybody know why plants, like flowers, make esters?
To attract insect.
To attract bees. That's exactly right. So this is called, you can actually make this in the lab. This is called methyl benzoate. It is synthetic, snapdragon scent. So when people make this in our 250, I think we do this in 255 or 256 lab. You can walk in when they're making this and it actually does smell floral because of the esters that are being released into the air. You can kind of smell almost like a florist shop kind of smell when they're doing this chemistry. If they haven't spilt any ether or anything that overpowers it. Okay? So the flower actually makes snapdragon scent through an SN2 reaction. Okay? It takes benzoic acid and it reacts it with a biological equivalent of iodomethane. There is no iodomethane in biology, okay? But there's a biological equivalent called SAM, acetylmethionine, okay? And it does the same kind of thing. It's just the leaving group's bigger. And that's how the plant makes its synthetic snapdragon scent, okay? But this is a two-step process. So it takes one reaction and two reactions to get to this, okay? There's an easier way to do it, okay? And it's called the Fischer esterification reaction. Fischer, F-I-S-H-E-R, I believe. Fischer esterification. So what's different about this reaction versus, or this set of reactions versus that reaction?
Doesn't have that LHO.
Okay, what would you say, Celine?
The alcohol is removed
The alcohol is removed? Okay,
from the beginning.
okay.
I just noticed that we were.
Yeah, we're comparing, that's right. This is one step, this is two steps. What kind of conditions are the first reaction here? Acid or base? Base. What are the conditions here?
Acid.
Acid. We just need a catalytic amount of sulfuric acid, but it's still acidic conditions, okay? And this actually is an equilibrium reaction. I didn't draw it as such there, but we're going to go through that. What does it mean when I draw over the arrow something like CH3OH? What does that imply to you?
Say the question again?
What does it mean when I write CH3OH over the arrow? What does that imply to you?
It means that something's getting added.
It is, that's true. Is it 1-to-1 benzoic acid and methanol?
No, a lot of methanol.
A lot of methanol. In fact, methanol is the solvent, okay? So I've got lots of methanol around. I've got just a little bit of sulfuric acid. So I'm going to write cat out beside it for catalytic. Okay? We do this very similar reaction all the time in my lab. We actually take the malonic acid that I told you about, we dissolve it in methanol, and we add like a milliliter of concentrated sulfuric acid. We heat it up overnight, and we get the ester, okay? Through this so-called Fischer esterification process. What do you think's going on in this reaction?
It looks like there's going to be an additional H added, making it, it's going to take that H and add another HO to it.
Okay. What was kind of the first thing that you thought of when we put sulfuric acid in anything? What's going to happen? Pardon? It will eventually make water. But oxygens typically like to get protonated, don't they? Right? And so we actually have an oxygen atom here. We've got an oxygen atom here. We've got oxygen atom there. And all of them technically can be protonated, okay? At different steps. But that's all a dynamic process. But what actually leads to a good reaction is I always think of sulfuric acid as how? H plus and HSO4 minus. And what happens is the oxygen of the carbonyl picks up a proton. That's the first productive step in this reaction. Now what can happen? Doesn't look like an ester yet, does it? Now what can happen? Do you think this pi bond is stronger now or weaker? Now that the oxygen is positively charged? It's weaker, right? So a poor nucleophile can attack the carbon. Methanol is an okay, I mean, it's a nucleophile, but it's a poor nucleophile. Now the methanol can attack and break that weak pi bond. And this too is a reversible reaction. Are we getting close to starting to look like the ester?
Slightly.
Slightly, right? I now have a CH3 group attached in there somewhere, don't I? But it's not an ester yet. Okay? So now what happens is called a proton transfer. And I always draw that just with a squiggly line and an H+. Because we're not exactly sure how it happens. Does the proton go to the solvent and then the solvent back? It probably happens a variety of different ways. Now I have that oxygen being positively charged. Now what happens?
The H2O leaves.
Does it just leave? Why do you say it leaves?
Because it's a good leaving group.
Water's a good leaving group. That's very similar to what we talked about in alcohols, right? But it doesn't just leave on its own.
And create.
The double bond will be regenerated?
Yeah. Now what happens? Does that look like an ester? A lot closer than it did before, right? What has to happen?
Just the hydrogen?
The hydrogen has to go, right? So we can think of our anion or solvent or whatever coming in and removing. Which is catalytic, so it comes back, right? Is that an easier reaction than the first one, or a more complicated reaction on your piece of paper right now? It's a lot more complicated. It's a series of 1, 2, 3, 4, 5 different reaction steps, right? It's actually a more complicated reaction than the SN2 mechanism we just talked about. But from the chemist's point of view, all I got to do is throw this in with methanol and add a little sulfuric acid. The rest of it takes care of itself. I don't have to sit and manipulate it. I just have to boil it for a while, okay? And then, of course, water. Oh, I forgot to throw on the water. Right. But it did leave, right? So if this is an equilibrium reaction, that means that if I have this, I can go all the way back to the starting material, right? At some point, I will build up a steady concentration of this and this. Okay? So how do I drive the reaction to go to completion? How do I get rid of all these reverse arrows?
Remove water and regenerate?
Yeah, I can remove water. Okay, there's a special apparatus that we have called a Dean Stark trap that allows us to remove the water. Or I can just add a ton of methanol. And that's usually what we do, right? Because this is a reactant. So if I have a huge concentration of this, it's going to drive the reaction to completion. Okay? It's called Le Chatelier's principle. Okay? If you had 107, you'll know about that. If not, I just told it to you, right? So we can perturb the equilibrium by adding a lot of this cheap methanol to make this this ester. And it turns out the way that biology makes this ester is through a thing called SAM. I told you that earlier. That's the iodomethane equivalent in biology. And it turns out if you were to buy that, it'd be like $100,000 a mole. So we're not going to synthesize it that way, are we? We're going to use cheap 45-cent a liter methanol, or dollar a liter, whatever it is, methanol. We're going to use a lot of it. We're going to drive the reaction to completion. All right. So what you need to know is that carboxylic acids can be used to form esters through either an SN2 reaction or through this so-called Fischer esterification reaction. And it can be any alcohol that's a primary alcohol or methanol. Okay, it works well with ethanol, it works well with methanol, propanol. When you start to get into the secondary or tertiary alcohols, a different mechanism is at play. Okay, so we're not going to worry about those. But the Fischer esterification is between a primary alcohol or methanol and a carboxylic acid, and it works pretty well. Okay, works. In fact, it's one of those reactions that I could take each and every one of you to the lab. You'd be able to do it. You'd get high yields. You can't mess it up. It doesn't require a lot of technique. Okay. Another derivative that is quite common for carboxylic acids are these so-called acid chlorides. Okay. So, for example, you can take butanoic acid and you can convert the OH into a chlorine. Okay. So this is an acid. This is an acid chloride, and we changed the name from oic acid to OYL, so butanoic acid to butanoyl chloride, okay? And so we've made what are called acid chlorides. Acid chlorides are useful because you can take an acid chloride and react it with other functional groups and make new molecules, okay? So you simply make acid chlorides by taking a carboxylic acid, reacting in it with thionyl chloride. You heat it up and you get the acid chloride plus hydrogen chloride gas and sulfur dioxide. It's a nasty little reaction. Produces these gases that'll make you gag and cough. So you got to do this kind of stuff in a hood because it generates that hydrochloric acid gas that's just obnoxious. But these reactions are actually very useful. So if I was to take butanoic acid and I wanted to react it with ammonia, let's say to make this so-called amide functional group, what's the problem with that reaction? Do you think that's going to work? It's not going to work. But yet it's this functional group right here that's responsible for the proteins in your body. Okay? So it's got to work somehow, right? Nature did it. What's the problem though? Ammonia, what is it?
Ammonia base.
It's a base. What's this?
Acid.
An acid. What do acids and bases do? Do they do that?
No.
They don't. They do this. And that ain't that. Right? Acid-base chemistry occurs. So how do we get around that problem? Well, if the acid's the problem, get rid of the acid. Right? How can I get rid of the acid? I convert it into what's called an acid chloride. This isn't acidic anymore. So now the ammonia can attack and ultimately give me my product. I'm not going to give you the whole mechanism, it's not important. I just want you to know why in the world we would want to make acid chlorides. So if this kind of reaction is responsible for making things in biology like proteins, do you think you have acid chlorides floating around in your blood? You do not. You do not. You have enzymes that do this chemistry. Okay? But nonetheless, even the enzyme has to do something to convert the OH into something that's a better leaving group. And it does that. It just doesn't make an acid chloride. Okay? Acid chlorides are actually quite toxic. Okay? They will kill you pretty easily. I keep thinking. All right. So that's chapter 13 stuff. And a little bit of 14. Let's talk a little bit about amino acids. What's odd about an amino acid? This is the general structure of what we call an alpha amino acid. We call it alpha amino because the nitrogen, or the amino group, is on the alpha carbon of the carboxylic acid. Okay? Alpha amino acids. What's odd about an amino acid when you just look at it?
Chiral.
They might be chiral. Most of them are, except for glycine. Okay? We'll talk about in a moment. But what else is odd about it? What do acids like to react with? Bases. What does this molecule contain? Both. It contains both an acid and a base. Pardon?
Has a carboxylic acid and an aldehyde.
It does, or an amine, yeah. Yeah, so we've got a carboxylic acid and we've got an amine. And you might be saying those should react with one another. And the answer to that question is they do. Okay? And we'll talk about that. But that's the odd thing about these molecules. They contain both an acid and a base. A good acid and a good base. Okay? So, your proteins in your body are made up of polymers of alpha amino acids that are linked together to form what are called peptides and proteins. Okay? When you ingest food, you have enzymes that break down proteins and peptides into the constituent amino acids so your body can use them. Okay? Put quite simply. And all of the amino acids, when you look at the alpha carbon, with the exception of glycine, where R is H. So glycine has 2 hydrogens. But all the others, the alpha carbon is chiral. It contains a carboxylic acid, it contains a hydrogen, it contains something else, and it contains a nitrogen. That's 4 different things around that carbon. And when you get into biochem, they're going to talk about L amino acids and D amino acids. Naturally occurring amino acids are the L form. And for the purposes of what we're going to be talking about here, the L form in all of the amino acids except one has the S configuration. Okay, so if I threw up an amino acid that wasn't glycine, okay, you would assume that the alpha carbon is of the S absolute configuration. The other one that is not the S is called cysteine, and it actually has a CH2 and a sulfur, and so that would take priority, and so you end up with the R configuration. But they're all called L amino acids. Okay? There are some bacteria that use D amino acids in their cell membranes so that your body can't recognize them and attack them. Pretty clever, right? So there are the opposite enantiomers in nature, but usually those are made and used by bacteria. Okay? Now, as we just said, carboxylic acids contain both an acid and a base, and so you would expect if you place this in water that it would just react with itself and it would form this charged species. Okay? And that's exactly what happens. So if I took glycine, where the R is hydrogen, and I threw it into water, I wouldn't have this anymore. What I would have is this. Okay? The acid, we've got a strong acid, we've got a pretty strong base. You're going to get that reaction to occur. Anytime you have opposite charges on the same molecule, we call these Zwitter ions. You might call it Zwitter. I frequently refer to that, but it's Zwitter. Okay? Zwitter ions. So we have something that's negatively charged and equally something that is positively charged within that molecule. It's called a Zwitter ion. Okay? So what's the overall charge on this molecule?
Neutral.
It's neutral. Yeah, it's neutral here, it's neutral there. But it does exist as this Zwitter ionic state. But the overall electrical charge doesn't change. Okay? All right. For the purposes of this exam, I highly recommend that you replicate these tables from your book into your notes. You are going to be held responsible for the structure of table 18.1's amino acids. Okay? I'm not asking you to memorize them at this point. But what I will tell you is that if you have them memorized before you start biochem, you will be in a lot better shape. Okay? And so what you will see is that we have the amino acids, right? There's the acid part, there's the amine part. This is in water at pH 7, so they're going to exist as zwitterions. They've drawn them all out as zwitterions. And notice the R group has changed. So if the R group is a methyl group, we call that alanine. Alanine is abbreviated as ALA or A. When you get to biochemistry, they are probably going to have you use the single letter code for all of the amino acids. I will be honest with you, I hate the single letter code, and I use the 3-letter code. So for my exam, the abbreviation that you need to know is the 3-letter code. I would put that in your notes as well. Okay? So alanine, glycine has just a hydrogen, right? No other carbon group. Isoleucine has this isobutyl group attached to it. Leucine has this group attached to it. Methionine has this sulfur and a methyl attached, right? So you've got all this. You've got phenylalanine. Anybody know anything about phenylalanine?
Is it not using drugs?
Well, technically, yes. Next time you get a can of Diet Coke, read the back of it. There's a warning. There's a warning on it for people who are phenylketonuria, meaning people who can't process phenylalanine-containing stuff very well. Okay, and it turns out that a decent size of the population is actually phenylketonuria, and they can't process phenylalanine properly. Okay, so but phenylalanine, of course, has an aromatic ring. Right, it's got a benzene ring attached to it. And it's a component of aspartame. That's the word I was looking for. That artificial sweetener contains phenylalanine. Proline. What's weird about proline? There's a ring, isn't there? And what do we know about the nitrogen? All of these nitrogens are primary amines, aren't they? What kind of amine is proline? It's a secondary amine. And it turns out that it plays a very important structural role in biochemistry. So you'll find prolines in certain places of a protein when nature decided to change how the protein is shaped. They will frequently throw in, or nature will throw in some prolines. You'll learn about that in biochem. Tryptophan, TRP, right, has this indole ring. This is an aromatic system, by the way. So we have aromatic groups in these. What do you all know about tryptophan?
Tryptophan seems like it's used in psychotics.
It is used in what?
Psychotics?
Might be, I don't know. There's one big myth about tryptophan, and we just finished the holiday.
Oh, wait, think turkeys.
Turkeys, yeah. Yeah, so
That's
it's
why it's up to 16
there's the myth that tryptophan causes you to be drowsy. It's a myth. If it were true, you would actually get drowsy every time you ate cheese. Because pound for pound, cheese has more tryptophan in it than does turkey. So why do we get tired at Thanksgiving? Because we spent all that time working, we spent all that time eating, and then we sit down to watch the football game and we fall asleep, okay? Tryptophan does not, there's no credible evidence that tryptophan actually makes you drowsy, okay? Valine, I always remember valine pretty easy because the side chain looks like a V on its side, right?
So. Isn't there a Latin sauce? Is that, Vatlin? Isn't there some that burns?
I don't know. You've also got other types of functional groups in the side chain. So here we can have an amide. This is asparagine. Where do you think that was discovered?
Asparagus.
Asparagus. That's exactly right. That's why it's called asparagine. Okay? It's three-letter code is ASN or N. Glutamine, serine has an alcohol. Threonine has a secondary alcohol. Okay, so these are some of the common amino acids that you all need to know. There are some that have carboxylates. Okay, here's cysteine. And again, even though cysteine has the L configuration, it is R because sulfur takes priority over the oxygens in the carboxylic acid group. And so based on the rules, this has to be an R configuration. Tyrosine, an aromatic ring with an alcohol, so it's a phenol. Lysine has another primary amine. And here's where I really hate, this is why I really hate the single letter code. It's K, right? If you look on the periodic table and you see K, what is K? It's potassium, right? And so I remember when I first took biochem and I saw this code and I was like, why is there potassiums everywhere? There's not. There are lysines, and so it's kind of confusing. Okay? And so with that, I think I'm going to stop for the day. My voice is about to give out. I'm sure you're tired of hearing me. So let me just, in the last couple of minutes, just talk about, again, the final exam will be Monday. It will be 50 questions. I have posted exam 1, the old exam 1 and exam 2 in Canvas for you to study. I will post exam 3 on Wednesday after everybody that still owes me an exam has taken the exam. Okay? I highly, highly encourage you to study the old exams. The final exam will not be a direct copy of the old exams, but it will be very similar. Okay? So what does that mean? It means I could have taken questions directly. It means I could have taken questions and been inspired and changed it around a little bit. It means I could have taken a problem and changed the numbers or the narrative. But you know what you saw on those old exams is what you'll see, the topics that you will see on the final exam. So those old exams will be a perfect, except for the new stuff, right? And the new stuff, I'm going to pull stuff from those assigned problems in chapters 13 and 18. So keep that in mind, and I will see you all on Wednesday.